Okay, hi everyone, welcome back. So we're almost there at the end of the semester, and I hope everyone is staying healthy, keeping safe, and your families are doing well. And so, like I said, we're almost there. We have 3 more chapters left at this point. I will not try to finish all the content in this chapters. My plan here at this point is to walk you through some of the fundamentals so that you can make connections with whatever we've learned so far in this semester and equip you with enough information so that you will do well in 3150. You're able to make connections between what you learn in 3140, take that knowledge and apply it in 3150 because it's going to be a continuation. So whoever you take 3150 with in summer or fall, they will keep referring to all the chapters in 3140, chapter 1 through chapter 10 or something, so that's going to happen. So at this point we have chapter 8, which deals with synthesis and reactions of alkenes, chapter 9 that deals with synthesis and reactions of alkynes, and then we have NMR left. So my plan as of this week is essentially to spend the next 3 lectures on synthesis and reactions of alkenes and alkynes, and we're going to do them as a combined chapter, and that's how I've been doing it for the past 2 times that I've taught 3140, because there's a good amount of overlap. And if you think about it, alkenes have 1 pi bond, alkynes have 2 pi bonds. So for the most part, okay, in a majority of cases, alkynes basically do the thing twice over. Whatever reactions alkenes do, alkynes do it twice over because they have 2 pi bonds. Okay, that is what happens. And wherever there are like differences or there are unique pathways that alkynes take, I will point those out. But again, like I said, my goal here is not to like overload you or burden you with all the content in the textbook. I will pick and choose some important reactions that I think that you must know going into 3150, and the ones that are useful for making this connection as you move into 3150 next semester. Okay, so that's the plan. And then the final lecture next week, I will keep that for discussing basics of NMR and proton NMR. So we will probably not go into carbon NMR, just proton NMR, discuss some basics of that. Okay, so we're going to start chapter 8 and 9 as a combined chapter. So alkenes and alkynes. And what we're going to do is most fundamental discussion would be based on alkenes, because once we understand what happens with alkenes, you basically take it and apply it to alkynes. Okay, that is what happens most of the time. So let's start here just by understanding the reactions of alkenes. Okay, what we know is, let's say if I draw an alkene, okay, this is an alkene. And if I were to ask you, would you classify an alkene as an electrophile or a nucleophile? Okay, because every discussion from chapter 7 onwards was going to be based on electrophile, nucleophile. We will bring in the concept of acid base as and when needed. And in 3150 also. So electrophile, nucleophile, we have to be very clear about these 2 concepts. Okay, so an alkene, is this an electrophile or a nucleophile? And again, electrophile would mean something that likes electrons or negative charge. Nucleophile would be something that likes a nucleus which is positively charged. So we are saying it likes positive charges. So if it likes a positive charge, that means it has electrons on it already. It is electron rich, because if it is electron rich, then it does not want more electrons because the electrons would cause repulsion. Okay, so given that, alkenes I hope most of you would agree that an alkene, the way it is, this would behave more like a nucleophile because it has this pi bond, which is basically an extra set of electrons. And also remember from chapter 1 that, when you have an alkene, it's a double bond. One of them is a sigma bond, the other one is a pi bond. And the sigma bond is a stronger bond. The pi bond is a weaker bond. And the pi bond is basically more electron density that's there between the carbon. So in most instances, an alkene actually behaves as an electrophile. Now let's see, sorry, behaves as a nucleophile, sorry. What happens, let's think about a situation where we have an electrophile along with our alkene, okay? So we have an alkene and we have an electrophile along with. That's why I've denoted that with E. Okay, the E represents an electrophile, and it's positively charged to say that it's a nice, good electrophile. Okay, so if in this situation we have a nucleophile, we have an electrophile, so I would think that the alkene, which is a nucleophile, is going to go attack that electrophile. And when you have an oxygen or a nitrogen, it uses its lone pair to go attack. In an alkene, that electron density is in the pi bond, so it uses the pi bond to go attack the electrophile. Okay, when it attacks the electrophile, I can see two situations emerge from this attack. The alkene attacking the pi bond in the alkene attacking the electrophile. There are two situations that would emerge. One possibility is that when this attack happens, okay, the pi bond is electron density that's shared between the two carbons. So when this attack happens, the electrophile has to get connected to one of these two carbons. So one possibility is that the electrophile is connected to this secondary carbon in my structure. Now, it may not be a secondary carbon all the time, but in this particular case, it is a secondary carbon. And when the electrophile ends up on the secondary carbon, this would leave a positive charge or a carbocation, result in a carbocation on that primary carbon. The other possibility is that the electrophile attaches to the primary carbon, and the carbocation ends up on the secondary carbon. Okay, now this is in a situation where your two carbons that are part of the alkene, they are different. One is primary, one is secondary. Okay, if they're both secondary or if they're both tertiary, then these two scenarios are going to be very similar, not identical, but there will be similarities between them. Okay, so we have two situations here, and I'm going to rephrase it slightly differently. Okay, because when I initially talked about it, I focused on the electrophile. I focused on where the electrophile is connected. Now I'm going to focus on this positive charge or the carbocation that's generated. So what we have here is when an alkene, and in some sense it is an unsymmetrical alkene, because there is one carbon that's more substituted than the other carbene. So when an unsymmetrical alkene reacts, or the pi bond of an unsymmetrical alkene does a nucleophilic attack on an electrophile, we have two situations here. One situation is where when we get the less substituted carbocation. Okay, so this is the less substituted carbocation, or we could get the more substituted carbocation. So based on everything that we know about carbocations, which one of these two is favored? And I hope everyone is saying at this point that a more substituted carbocation is more stable, so that's preferred. This is less likely to happen, okay? So the top pathway which leads us to the less substituted carbocation, that's going to be an energetically unfavorable process or an unfavored process, whereas this bottom pathway that leads us to the more substituted carbocation, that's a favored process. And this is what we usually observe in reactions of alkenes. So we're going to see this like over and over again through the reactions of alkenes, okay? So we considered one step where an alkene reacts with an electrophile and we get a carbocation. Now, imagine that there is a nucleophile now. There is a nucleophile in our system, okay? So there's some other nucleophile at this point. What would happen between these two? So now we have a carbocation, which is electrophilic, and we have a nucleophile. So what's going to happen is the nucleophile is going to go and attack that carbocation, okay? The nucleophile attacks the carbocation. And what would result is something like this. We're going to get a structure where this electrophile and the nucleophile are both connected to these carbons, okay? The carbons that were part of the pi bond in the alkene. The electrophile and the nucleophile get connected to those carbons. And what you notice is the nucleophile is connected to the more substituted carbon, and the electrophile is connected to the less substituted carbon, okay? This kind of a product, regiochemistry, that means where is the nucleophile, where is the electrophile, okay? This kind of a product regiochemistry is called a Markov-Nikov, so Markov-Nikov addition. Okay, Markov-Nikov addition. In fact, the reactions of alkenes in general are called addition reactions because what happens is you break the pi bond, okay? You break the pi bond that would create a valency on both carbons that are part of the double bond, and you add things to those carbon atoms. So this is pretty much like two things adding to those carbons by breaking the pi bond. So the pi bond becomes a sigma bond. Sorry, no, the pi bond doesn't become a sigma bond, it becomes two sigma bonds, okay? The pi bond breaks and it forms two new sigma bonds with the nucleophile and the electrophile. The sigma bond remains, okay? So we go from like an alkene to an alkane, okay? That is what's going on here. So that's basically everything. Kind of I've broken up everything, you know, I've basically like split it up, you know, so that we can see this. Now this is not how we're going to see things. I'm going to draw what is it that we're going to see usually, okay? Okay, I think we have everything that I would like to see in that portion here. And now let's see a situation that we are more likely to encounter, okay, in the reactions of alkenes. So what we're going to see is we're going to have alkene and we're going to have reagents that look like this, okay? So we will have an alkene and we are mostly going to have reagents which would have an electrophilic part and a nucleophilic part in them. And the electrophilic part is the portion which is del positive. The nucleophilic part is the portion that's del negative. Okay, and so in most of these reactions, what's going to happen is the alkene, it begins as a nucleophile. The alkene would use its pi bond to attack the electrophilic part of the molecule. And when that happens, it would kick out the nucleophilic part. And this would lead us to a carbocation. And we already talked about which carbocation is more likely to form. So the more substituted carbocation is more likely to form. And so we get that carbocation, which in this particular case is secondary, but that is the more substituted carbocation. So we get that. And along with this, we're going to have the nucleophile. Okay. Now, we have a carbocation, we've got a nucleophile. And so what happens is the nucleophile would go and attack that carbocation. And so our final product is the addition product, where both the nucleophile and the electrophile add to the carbons that were originally double bonded with each other. So both the electrophile and the nucleophile will end up here. And so what we are looking at here is an addition product. Okay. And since these reactions initiate, okay, this is where the reaction starts. They initiate by the attack of the alkene as a nucleophile on an electrophile. These reactions are called electrophilic addition reactions. So the reactions of alkenes are called electrophilic addition reactions. Okay, there's something else that I want to point about here, because stereochemistry is something else that we have to keep in mind. And we have to talk about that carbocation. So going back to carbocations, okay, realize that a carbocation, I can, that this carbocation carbon, okay, that carbon is sp2 hybridized, which means the geometry around that carbon should be trigonal planar. It should be trigonal planar. So I can represent okay, because there is also a hydrogen at that point. Okay, remember that there is a hydrogen here. I'm drawing out that hydrogen here. And what we have here is this electrophile. So this carbocation on this carbon, the carbon is trigonal planar, and going back to chapter 1, there is an empty p orbital here on that carbon. That is what a trigonal planar carbon looks like. That's pretty much what we saw for radicals also. Radicals are also sp2 hybridized, okay? And they have a p orbital, but in that case, the p orbital is not empty. It has an unpaired electron in that p orbital. In case of a carbocation, this is an empty p orbital. So what that means is now, when this carbocation is attacked by the nucleophile, because this is a p orbital, okay, with 2 lobes, which is on that carbocationic carbon, the nucleophile now, and we'll use appropriate colors here. So the nucleophile when it's attacking that carbocation, it could attack that carbocation from the top face, or it could go and attack the carbocation from the bottom face. Okay, it could interact. The nucleophile could use its the electrons on it. Okay, those can interact either with the top face or the bottom face. And so what that means is, when we get our product here, we are going to get two possible. Sorry. This trigonal planar, after the attack, it's going to become tetrahedral. So if the nucleophile attacks from the top, then the R is going to be here, the hydrogen is here, our nucleophile is over there, the electrophile is here. That's one possibility. Plus, you're going to have a situation when the attack happens from the bottom face, then the R and the hydrogen are going to be flipped up. The nucleophile is going to be attached from the bottom face. The electrophile is still where it was. And now, as you can notice, this carbon here is chiral. In fact, it was chiral right here, okay? Because even here, this carbon is chiral because it has an R, it has a hydrogen, it has a nucleophile attached to it, and it has another group connected to it, okay? So that carbon becomes chiral. Now, this may not happen in every scenario, okay? Not with every molecule, but whenever this is possible, then you're going to show this. And so what that means is, what we get here, okay, we are looking at two enantiomers here. So what we get from these reactions is a racemic mixture, okay? So pretty much like attack on a radical, when the nucleophile attacks that carbocationic carbon, if that carbon in your product is chiral, then you're going to make enantiomeric products. Mixtures of enantiomers, equal amounts, because it's planar, so there's no control over where the attack happens from. And what we would end up with is a racemic mixture. Okay, so that was basically an overview of what we are going to see throughout in the reactions of alkenes. Okay, so that kind of captures and summarizes everything. And now what you're going to see in the reactions that we do is just basically a repetition of this concept, but applied to different reagents. In every case, our reagent that we use is going to be different. So we'll have molecules which have electrophilic portions and nucleophilic portions in them. In most cases, okay? In most cases, we're going to see that. And we're basically going to see this repeated over and over again. There are exceptions, okay? There are exceptions where the reactions do not follow this pathway. I will bring those to your attention. But in most cases, this is what we're going to see. Okay, so that's an overview of what we're going to see in chapter 8, and alkynes, as and when we get there, I will point out similarities and differences. Okay, bye.